So we shall deal with the next concept is introduction to Vhdl. I think this is the remaining part of the fourth module, Vhdl. So what do you mean by Vhdl? HDL refers to hardware description language. Okay, V refers to very high speed integrated circuit. Okay, in this chapter we're gonna learn about how to represent the gates, and by using Vhdl represent gate and combinational logic by concurrent Vhdl statements, and we're gonna learn about how to interconnect Vhdl components and how to simulate the Vhdl module. So basically, why do you need Vhdl? As I just told, Vhdl refers to very high speed integrated circuit hardware description language. V refers to very high speed integrated circuit. H refers to hardware. D refers to description. L refers to language. So in short, we call it as Vhdl. So why do we need Vhdl? Okay, when it comes to the circuits which is of bigger in size and more complex, which contains about thousands of gates, it's not easy to construct such circuits, but we have to construct the circuit at the end. But the thing is, first what they do is they simulate the things. Simulate is nothing but the virtual behavior which works exactly as that of the reality. It will work exactly the real thing, okay? But it's a simulation. So why do you need simulation? Because when you construct a circuit which is containing up of thousands of gates, after if we go wrong somewhere else, so we won't be knowing where exactly it went wrong, right? It will be very hard to debug the things. So rather than going to the real thing in one stretch, what they do is they will first construct a simulation. Once they get to know that everything is fine, then they start to building the real thing. Okay, digital systems that work with, that is what they are given. Look at here. Digital systems have continued to grow in complexity. As digital systems have become more complex, detailed design of the systems at the gate and flip-flop level has become very tedious and time consuming. For this reason, the use of hardware description language in the digital design process continues to grow in importance. Okay, I hope you people came to know why we need to use Vhdl. So Vhdl, we have two hardware description languages. One is Verilog and one is Vhdl. Okay, two types, Vhdl and Verilog. Okay. So V refers to very high speed integrated circuit hardware description language, right? Okay, complexity is the same thing they are written. Okay, in case of Vhdl, we can write the programs in three manners. One is up of three different levels. One is behavioral, second one is data flow, third one is structural. So what is behavior, what is data flow, what is structural? So you can just imagine the adder. In the previous classes I told about half adder, full adder, adding the things, binary adding. So 0 and 1s are the binary things, right? We are just adding 0 plus 0 or 0 plus 1 or 1 plus 1 or 1 plus 0 like that. That's a binary adder, okay? In that binary adder we compose half adder, full adder like that. So for example, a binary adder could be described at a behavioral level in terms of its function of adding two binary numbers. So if you want to represent a binary adder, then it has to be separated into components, and the components has to be interconnected. So you will get to know what is component, how the component need to be interconnected, all those things, okay, later. That's behavioral model. So if you want to implement the same adder in case of data flow, so that can be implemented just by writing the logic equation. How this adder works, you just need to write the logic equations. Like C program, you write the equations, right? Like logic, right? You just need to write the logic. If you have written the logic, then it is fine. The program works. That is data flow model. Okay, and we are left with structural. In case of structural model, so So we need to specify the interconnection of gates which make up the ladder. So we need to explicitly specify, clearly specifying one by line. So which gate has been connected to which gate, or what each gate performs, each and everything has to be specified clearly in case of structural model. Okay, so in your examination they might give a circuit and they might ask you to write a they will definitely ask you, they will definitely give a circuit and they will definitely ask you to write a Vhdl program. So they can explicitly specify you need to write structural model or behavioral model or data flow model. It all depends upon them. If they don't specify anything, you can write the program on your own. I mean, you can choose behavioral model or structural model or data flow model. It all depends upon you people. Okay, so let me go how this works. Look at this circuit A, B, C, D, and this is an AND gate, this is an OR gate. Okay, if you want to write this circuit in a data flow model, it's basically very easy. See here. So this is AND gate, A and B are the input, C is the output, right? So the values of A and B will be passed on to this gate, and the output it will be assigned to C. Okay, C, A and B assigned. This is an assignment operator. A and B assigned to C. Okay, so the right side the evaluation part, and the left side the will be assigning the value. Okay, so once you get the C value, C and or D assigned to E. Okay, after 5 nanoseconds, what is this 5 nanoseconds? The time taken for a signal to transmit through the gate. Each and every gate, as we came to know that each and every gate will be having some delay, right? So what is the delay? After 5 nanoseconds, each gate will take 5 nanoseconds. They have explicitly specified 5 nanoseconds. If we don't specify 5 nanoseconds, or what is the time taken, what is the delay, so by default the system will take it as delta. Delta means 5, basically take it as 0. That is nothing but the delta operator. Delta is something like, it looks, this is delta value. Okay, if you want to represent the same in the behavioral model, this is how you are supposed to write. A and B, the output of A and B is worked with D or this one, D or C, and finally it will be assigned to E. So this is behavioral model, single line. This is 2 line. So this is an instantaneous statement 1 and this is an instantaneous statement 2. In case of data flow model, we come across instantaneous statements like 1, 2. So this is one component, this is one component, and this is one component. So these two are interconnected in case of data flow model. So behavioral model, within a single line we are going to write the complete logic. A and B, the output of this one will be ORed with D, and the final will be assigned to E, like this. Here parentheses, look at here, parentheses are used to specify the order of the operator execution. Okay, so let me assume this is what the gate it is, right? This is E, this is A, this is B, this is C, and this is D. Okay, so as we know, this is it takes 5 nanoseconds. This takes 5 nanoseconds. Let me assume like this is 1, this is 0, this is if this is 0, this is 0, and finally it will be 0. 1, 0 in case of AND gate is 0. So 0 plus 0 is 0, OR gate, right? This is. So suppose if I change this B to 0 to 1, 1 and 1 will be, C will be 1. So it will take the B will change from 0 to 1 in 0 nanoseconds. Okay, so this change need to affect C. So C, before it was 0, it has to convert to 1 now. So conversion from 0 to 1, it takes 5 nanoseconds. Okay, once the change occurred in C, that is value 1 and 0 will be 1. So the change affect E from 0 to 1, again E will take totally 10 nanoseconds. Why? 5 nanoseconds here, 5 nanoseconds here, so totally 10 nanoseconds. So the finally for E to change from 0 to 1, it take 10 nanoseconds. So this is how it works. Okay, so this is what they are given. So if you want to represent the same program with a structural model, we are supposed to write the instantaneous statements. instantaneous statements are used to connect, specify how the components are connected. So look at this. This is instantaneous statement 1 and this is instantaneous statement 2. Gate 1. This is what gate 1 and gate 2. Okay. And 2. This is a name given to the gate. And 2. This is a name given to the gate. Port map ABC. ABC. AB refers to the inputs. AB refers to the inputs and C refers to the output. So like AB refers to input and C refers to the output. Similarly, CDE. CD refers to input and E. This is R2. R2 is the name given to this gate. And 2 is the name given to this gate. So this is the names, and 2 and R2. You can give any name. You can give your name also. No matter. No issues. Okay. Gate 1. So what happens? Port map. The port map of a gate 1 connects A and B to the AND gate inputs and connects C to the AND gate output. Similarly, C and D for the AND gate inputs OR and E to the OR gate output, like this. Okay. This is how you're supposed to write the structural model. Okay. Vhdl simulator monitors the right side of each component statement, and that any time a signal changes, the expression on the right side immediately re-evaluated. So this is what this is a Vhdl statement. This is right side. Okay, it monitors any the values change towards the right side, it will get evaluated and it will affect the C. Okay. Right side immediately re-evaluated. This is what we are. Okay. Suppose in case if we don't say, look at these two statements, C is equal to A and B assigned to C, C or D assigned to E. So we have not specified any delay here. So before here we have specified delays 5 nanoseconds, 5 nanoseconds, right? But here we don't have any specified delays. If we don't specify the delays, the propagation delay will be taken as zeros. The simulator will assume the delay referred to as delta. Okay, A is equal to 1, B, C, D is equal to E, 0. If B is changed to 1 at time 1 nanosecond, then the C will change to time at 1. Okay. So this is what, so they are given. So let me assume they have not given any delay. Okay. So let me write 1 second. So this is basically A is equal to 1, B is equal to 0, C is, if A is equal to 1, B is equal to 0, C is obviously 0 and D is equal to 0. So 0 plus 0, E will be 0. Okay, this is basically the first thing. Okay. B, which now A is equal to 1, it remains as it is. B will change to 1 now. Okay. So as I just told, if we have not specified any delay, it will take it as delta. Okay. So if B takes to change from 0 to 1, if it takes to 1 nanoseconds, if B takes to change from 0 to 1 nanoseconds, then C will be, what is the delay here? So delta plus 1. Why delta plus 1? Delta is the delay here, plus B take 1 nanoseconds. So the total time taken for the C to change from 1 to 1, from 0 to 1. C changes from 0 to 1. Why? Because B changes from 0 to 1, 1 and 1, the output will be 1. Before the C was 0. So the time taken by C to change from 0 to 1 is delta plus 1. Similarly, now this C is 1, D is equal to 0, 1 plus 0 is E is equal to 1 now. So E has to change from 0 to 1. So the time taken for E to change from 0 to 1 is delta plus 2. Why? 1 nanoseconds here. So 1 nanoseconds here. So to change. So 2 nanoseconds. So delta plus 2. This is how it works. So there, that is what they are given. Delta. Okay. So this is a signal assignment operator. This is a signal assignment operator. So their syntax is signal name. Here the signal name is C, and expression. The expression is A and B. Okay. After delay is the amount of time taken to change. This is a syntax for a signal assignment operator. Similarly, in case of C programs, you come across explicit loops, while loop, for loop, and some statement which need to be executed repeatedly. So what do you need to do in such cases? The same here, we don't have any explicit loops, but if you want to execute some statement repeatedly, what that can be done is, like, look at this. We have a feedback line for not. So if you assign 0, 1, so if you go to 1, this will be 1, now it will be 0. If 0 is passed, 0 to 1, and 1 it will be passed, so 1 will be changed to 0, like 0 1 0 1, the loop. So this can be written as clock. Clock is a signal name assignment operator, not clock. Why not clock? If clock is 0, not clock will be 1. So if 1 will be assigned to clock, this will be changed. So again, not clock, it will be 0, like this, after 10 nanoseconds. So 10 nanoseconds means each time the NOT gate will take 10 nanoseconds to change from 0 to 1 or 1 to 0. So it will be keep on looping like this. Okay, if we have not specified 10 nanoseconds as the delay, it will take it as delta. First 0 plus delta. For the second iteration, 0 plus 2 delta. For the third iteration, 0 plus 3 delta, like this. Okay, it will be keep on looping the things. Okay, so then we have Vhdl is not case sensitive. Okay, case sensitive means you can write small letters or you can write capital letters, it doesn't matter. So look at here, see, they have written small, they have written capital, both are one and the same, the execution doesn't differs. And as in C, so if you want to define identifier, there will be some specific instructions. Similarly, if you want to define an identifier here, so two things that are not supposed to be done. Always the identifier name should start with a letter. That is the first thing. That's a condition. And the identifier name should not end with a underscore. These are two conditions which need to be followed. First thing is the identifier name should or must start with the letters. That's the first thing. Second thing, it should not end with the underscore. These two things should be kept in mind while defining the identifiers.